We've made it to chapter 22, quite an accomplishment. And this chapter in particular presents the significance test of Pearson's R, and then presents a variety of other tests. And also it examines appropriate procedures in single case designs, talking about what these designs are, and in qualitative research. And we do some work on reasoning with data as the chapter concludes, and then also the topic of data transformation comes up. The test of Pearson's R examines whether the correlation in a sample is likely to be due to chance alone. The basic idea would be that even when the population correlation, symbolized by rho, equals 0 due to sampling error R almost always would differ from this amount. So is the correlation that we see in our sample one that's likely to be due to chance alone? What does the p-value from a non-directional test of R convey? It would convey, given a population of correlation of 0, given that rho equals 0, the probability of obtaining your particular value of R, the R that you obtained in your sample, or of obtaining an R with an even larger absolute value. Our hypothesis pair can be either directional or non-directional. I'll read the non-directional pair for you. The correlation in the population from which the study sample was selected equals 0 is the null. The alternative is the correlation in the population from which the study sample was selected does not equal 0. And here are our two possible directional pairs. So for instance, in this one, H1, the alternative hypothesis states that the population correlation is greater than 0. And you would use this one in a situation where you strongly suspected that that was indeed the direction of the population correlation, and therefore of the value of R that you would obtain in your sample. This test assumes normality, but it's going to be reasonably accurate when n is greater than or equal to 15, even in the case of strong skew. Our degrees of freedom are going to be n minus 2. When the hypothesis pair is non-directional, our test of R is a two-tailed one, and here's the decision rule in that situation. Fail to reject the null if the absolute value of the obtained R is less than the value of R in the table of critical values of R. On the other hand, we will reject the null if the absolute value of the obtained R exceeds the R in the table. And let's go ahead and read the hypothesis pair when the alternative states less than. This is one of the examples of a directional pair, obviously. So when the alternative states less than, you would fail to reject the null if the obtained R exceeded the negative of the R in the table of values, and you would reject the null if the obtained R was less than or equal to the negative of the R in the table of values. The table of critical values, it lists only positive values. For instance, if we saw a value of 5, now that would not be in the values in the table, because values of R are going to range obviously between -1 and 1, but the negative of 5, for instance, is -5. So that, for instance, the negative of 0.42 would be minus 0.42. Okay, our example will come from the special needs adoption study. In that study, the correlation between family income and closeness of parent-child relationship as conveyed by a 4-point scale in a sample of where n equaled 635, correlation was minus 0.21. First step is to state our hypothesis pair. I'm going to use a non-directional pair. As you know, I favor these in situations where we don't have really strong expectation regarding direction. So our null is that in the population from which the study sample was selected, the correlation between family income and closeness of parent-child relationship equals 0. And our alternative is that this is not so. Here is the null and alternative expressed with symbols, where this is the symbol for rho, the population correlation. The second step is selecting the significance level. Let's select the 0.01 level. We have a very large sample size. Using the 0.01 level will reduce the likelihood that an association that's trivial in size will achieve significance. So it's tougher to reject at the 0.01 level than at the 0.05. And so to some degree this will counterbalance the fact that our power is going to be quite large given our very large sample size. So since we've got large sample size and therefore fairly easy to reject the null given that large sample size, we'll use the tougher significance level and counterbalance that. We are simply going to use statistical software to carry out the test, so that I went ahead and used the SPSS software, and the P from the test expressed exactly was 0.000006. I'm not sure if that's 6 times in a million or something similar to that. Obviously this p-value is very, very low, and we are going to reject the null. The probability that our difference is due to chance alone is a very, very tiny one. Now, interpreting our results a little bit differently, given a true null, in other words, if the population correlation is 0, the probability of obtaining a Pearson's R that is less than minus 0.21 or greater than 0.21 is 0.000006. So these are the results that are as extreme as our result or even more extreme. So in sum, we reject the null. As you begin to do data analysis, you will use computer software to carry out significance tests, such as the test of R. But the text does have a table of critical values of R at the back. We have 633 degrees of freedom. Our sample size of 635 minus 2 is 633. Now, if a table of critical values of R does not list the exact degrees of freedom, one uses the row with the next smaller number. So we have 633 degrees of freedom. The row with the next smaller number, the closest smaller number, is the row here with 602 degrees of freedom. A sample size of 602 and 600 degrees of freedom. So we are using the 0.01 level. In other words, we have set alpha to 0.01. Here is the critical value of R in the table. So in other words, with a two-table test, we would be rejecting if our obtained R in the sample was either greater than 0.105, or on the other hand, we would also reject if that correlation was less than minus 0.105. The absolute value of our correlation, which was minus 0.21, is 0.21. I mean, that is indeed greater than 105, and so by the decision rule for the non-directional hypothesis pair, and thus the two-tailed test, we reject the null, and we reach the same conclusion as we reached using the computer. Our correlation is indeed unlikely to be due to chance alone. Presuming that the table is correct and that the computer program is correct, and there's every reason to think that they will be, I mean, you'll always reach the same conclusions with the table or with the computer program. And the advantage of the computer program is, among other things, that it yields exact values of p rather than only telling you whether the p is greater than or less than some given value. Before we go on to the next slide, I mean, let's just take a look at the critical values of R, say where alpha is equal to 0.05, for sample sizes of given amounts, different sample sizes. So do observe that the absolute value of R that is required to reject the null decreases as sample size increases. So as sample size goes up, smaller and smaller differences from the value stated in the null, in other words, from 0, become sufficient to reject the null. And so this is demonstrating, other things being equal, as your sample size goes up, so also does your statistical power. This slide is demonstrating the just made points visually. So the top distribution is the sampling distribution for R when sample size is 20. And this is demonstrating the rejection regions for a two-tailed test. And you can look and you can see that, oh, I'm going to say this is about minus 0.47 defining the negative tail and 0.47 defining the positive tail. So you need absolute value greater than about 0.47 to reject given sample size of 20. Now if we up the sample size to 50 and we continue with a two-tailed test, then you can see that the rejection regions are coming closer to 0. So smaller absolute values of R will now reject the null. Looks to me like the value that will reject the null now is about 0.27. In the distribution C here, we've now upped sample size to 200, and just to demonstrate a one-tailed test, we're presenting a one-tailed test here in which the alternative hypothesis states less than. You see how the sampling distribution here is narrower than is the case in our middle distribution, which in turn is narrower than in the smallest distribution conveyed at the top. So again, it's conveying that values of R closer to 0 will now reject the null. So here the value that rejects the null looks to me to be about minus 0.13. So in this situation, a fairly small difference rejects the null. In some, as sample size goes up, the sampling distribution becomes narrower. Smaller differences from 0 become sufficient to reject the null. It's certainly getting easier to reject the null, and indeed power is increasing. A correlation matrix presents correlations between a set of variables. So the correlation presented here are correlations among 5 variables in the special needs adoption study. Now, the line that I'm tracing right now, well, this is often called the diagonal of a matrix. And in a correlation matrix, this diagonal is presenting the correlation of each variable with itself. And so these correlations are 1. I mean, it is indeed always the case that a variable correlates perfectly with itself, a perfect positive correlation of 1. So in essence, there's no information here in the diagonal that we would examine. Note that each correlation is presented in the correlation matrix both above and below the diagonal. As an example, the correlation between income in thousands and behavior problems is 0.092, and that can be found in this cell, and again that very same information is presented in this one. I think my eye is drawn to the strong correlation between behavior problems score and parent-child relationship scale score, correlation of about -0.61, so that's a very strong negative relationship. So I mean, what researchers do is explore different correlations, trying to see which ones are larger or smaller than might have been predicted, perhaps. But computer programs easily generate correlation matrices for you, and this is a simple correlation matrix, and you'll see you can develop some fancier ones as well. Now, we will indeed present some more significance tests as we go through the last couple chapters here, but significance test of R is the last one that we will cover in detail. Any that we cover from this point forward, well, essentially I'll tell you the big ideas behind the test, but we won't go through them in detail. Now we take a bit of a detour here just to talk about the hypothesis testing model. And this text has taken the position of presenting a formal hypothesis testing model with 4 steps. See if I can do these steps from memory. I mean, you would state the pair, you would choose the significance level, you would carry out the test, you would make your decision on the hypothesis pair. Now, in the formal hypothesis testing model, a study result is significant at the level that the researcher selects. So look at this example. Suppose that we select the 0.05 level, which is to say we set alpha to 0.05. Now suppose that the p is 0.007. Note that this value of p is less than 0.01. So in the most formal sense, even though this p is less than 0.01, we don't report it as less than 0.01, but rather we report it as less than 0.05. In other words, we report it as significant at our selected level. Now, in real-world research, things are not that formal. That just isn't the commonly followed practice. In real-world research, significance is reported at the lowest achieved level. So, for instance, were you to select the 0.05 level and your p-value came out to be 0.007, you would go ahead and report that result as significant at the 0.01 level. I mean, more informally, in real-world research, oftentimes, indeed most often, researchers don't bother to select a significance level ahead of time. They don't bother to do so because they're going to report the level as significant at whatever level it achieves. For instance, our p of 0.007 achieves significance at the 0.01 level. Now, further, as you know, the computers calculate precise values of p, and the American Psychological Association's manual recommends reporting, whenever space permits, actual values of p rather than just levels of significance. So in the above example, you would report that p equals 0.007, and I endorse this too. The hypothesis testing model presented in the text is providing guidelines to help you step forward through the steps of hypothesis testing. But I mean, it's the case that most of the time researchers don't state the formal steps. I mean, they simply carry out the given statistical procedure using the statistical software. And oftentimes you'll read about results, and there will not be formal presentations of the hypotheses. The next video is going to begin with the exploration of parametric versus non-parametric significance tests.